Okay, let's finish up 1.4, cosets and counting. We've got 3 additional results to prove to wrap this up. So we're following on the heels of Lagrange's theorem. For G a group, H and K subgroups of G, subsets, I guess we'll do it in general, we'll define the set HK where lowercase h is an element of set capital H and lowercase k is an element of set capital K. We're denoting this as capital H times capital K, which seems reasonable. It's defined for sets. We'll only consider what happens when those sets are themselves in fact groups. But even in that case, H and K can be subgroups of group G, and H times HK, that set still not be necessarily a subgroup of G. Products of subgroups aren't necessarily subgroups. Intersections of subgroups are, for example. We've been through that. But we may not get a subgroup out of this, but it's a set. It reminds me a bit of cosets in the way that the products are taken, maybe. But we're going to look at cardinalities of these sets as follows. Theorem 1.4.7 says, let H and K be finite subgroups. So we are doing the group setting because we will look at cosets of groups. You can only look at cosets of subgroups. There aren't cosets of sets. That wasn't a thing. So H and K are, in fact, subgroups. Then the cardinality of HK is claimed to be the cardinality of H times the cardinality of K divided by the cardinality of H intersect K. Of course, the big word there, I hope I called attention to it. I hope I said it. It's finite. These have to be finite subgroups. We wouldn't be talking any sort of division unless we had sets of finite cardinality. Multiplication of cardinal numbers makes sense even when they're infinite, but division of cardinal numbers doesn't, unless we're dealing with finite cardinality sets. So that's why the finite hypothesis there. Not a terribly surprising result, but let's go through the proof, which is based on coset information. Okay, so setting is H and K, finite subgroups, and a claim about cardinality. So define C to be H intersect K. You know, because it's corollary 1.26, intersections of subgroups are again a subgroup. So C itself is a subgroup of G. As long as we got subgroups, we can talk about cosets. Lagrange's theorem would tell us the index of C and K, so we're dealing with a finiteness here, that is the number of cosets of C and K, would be the cardinality of K divided by the cardinality of C. It was the furthermore comment of Lagrange's theorem that dealt with the case of having finite groups. C, we defined to be H intersect K, so we'll replace that here to get this cardinality. Cardinality of K divided by the cardinality of H intersect K. Let's denote that as N. So we've got K as a disjoint union of the N cosets of C. You know, the cosets partition the group, the little subgroup is C in this case, and the big group in this 2 or 3 lines of argument is group K. So we're taking group K and partitioning it into cosets of subgroup C. We know there'll be N of them. We just define the index to be N, and the index is the number of cosets, you know, wink, the cardinality of the set of cosets, as it were. But here we've got the finiteness, so I don't have to be apologetic about saying number of. And you know these things partition up the group, as we saw earlier. So K is a disjoint union of, say, C K sub 1, union C K sub 2, up through C K sub n, for some K sub i's, K1 through K sub n, chosen from group K. We call this a set of representatives of the cosets earlier. So we're doing that thing again. So these K1 through K sub n's are chosen in a special way. We get the disjointness here. The K sub i's are distinct, for one thing. Okay, so we want to do some counting still. We've introduced the cardinality of K divided by the cardinality of H intersect K. So that's a piece of the plan here. So remember, this is the goal. Next, we want to consider the sets H, C, K sub I. So we're taking a product as defined previously, HC. So this is a product of all elements of H times elements of C. In addition to that, we're multiplying it by K sub I. So we're considering this bunch of sets. No problem. May not be a group, but it's a set of elements in the big group capital G, right? All this is happening inside big group capital G. All the binary operations are defined because everything happens inside group G. This is totally a conversation really about those subgroups though. So we're defining these sets, and what we're ultimately going to show is these things are disjoint and they form a partitioning as well of something or other. First, assume HC K sub I intersect HC K sub J is non-empty. So suppose this collection of HCK sub i's as I ranges from 1 to n, suppose it isn't a disjoint collection. So suppose we get an intersection, we're about to get a contradiction a few lines down the road. So we're showing disjointness. Suppose they ain't disjoint. Then there's a thing in here that's also in there. That is, there's a H1C1 K sub I that equals some H2C2 K sub J, an element of this set, which would be of the form element of H times element of C times K sub I, say H1C1 K sub I, taking H1 from subgroup capital H and C1 from subgroup capital C, and then the K sub I on the right. And then similarly, this equals some element of H, capital C, K sub J, which would be something of the form H2, C2, K sub J, H2 and C2 from capital H and capital C, respectively, the obvious thing. So we'd have an inequality like this if there was overlap. The beauty of having this is now I could manipulate elements instead of manipulating sets. We can get the, say, the K's on the left and the H's on the right. So do some inverse multiplication by inverses, bring the K sub J to the right-hand side. We'll get C1, K sub I, K sub J inverse. Take the H1 to the right-hand side. It'll have to stay on the right-hand side of the product. We're multiplying both sides by H1 inverse. The right-hand side of that little equation becomes this. Claim is we've got ourselves something in H. Well, that's because H1 and H2, so H1 inverse and H2, are elements of H. C2 is an element of C, but C is H intersect K. C is a subset of H, so C2 is also in H. So element of H, element of H, element of H. So the products we get also as an element of H. So this left-hand thing, by the way, is an element of H as well. C1 inverse is in C and so in H. So we're going to take C1 inverse, multiply it by this thing, which we know to be in H. It would be a product of two elements of subgroup H. So again, giving us something in subgroup H. All right, so we took a C1 inverse, multiplied it by this. C1 inverse, C1, associativity, and all of that will leave us with a K sub I, K sub J inverse, something in subgroup H. But K sub I, K sub J inverse, well, this is definitely in K. In K sub I and K sub J are from K. That's why we use those symbols. So we've got that this K sub I, K sub J inverse is in both H and K. C was the intersection of H and K from line 1 up here. So K sub I, K sub J inverse being in both H and K is also in C. All right, C is a subgroup of everything we're talking about. It's a subgroup of H, it's a subgroup of K, it's a subgroup of G as well. But anyhow, it's a subgroup. When you have the relationship K sub I, K sub J inverse in C, we can describe that, if you like, as K sub I is right congruent to K sub J modulo subgroup C. So we got right congruence here. Hey, when you got right congruence, you've got right cosets equal. Corollary 1.4.3 part 3 said exactly that. So we've got right congruence of K sub I and K sub J modulo C. So we get the right cosets CK sub I and CK sub J are the same cosets. But we had these things disjoint. These came to us as cosets in a setting such that we know we get the disjointness up there. Well, you ain't getting the disjointness down here. So this contradicts our hypothesis, or I'm sorry, this is a contradiction which shows our hypothesis that this set intersect that set is not empty, is false. And these two sets must be disjoint. We had the setting that the I's and J's were different. So we're getting disjointness of these sets up here, and there's a proof by contradiction. HC, K sub I, HC, K sub J are disjoint for distinct I and J. Okay, so we're still looking at this, we're still trying to count something up here. HC is the same as H. Yes, C is a subgroup of H. So if I take H and multiply it by everything in here, I'm not going to get anything outside of H because these are all in H. Closure of H is a group. If you like, the identity is contained in C. So we get out everything that's in H. So we get this set equality. So remember what we're trying to show, cardinality of HK. Let's talk about HK. So the set HK, that'd be the set H times this product of cosets. The previous slide, we wrote K as this disjoint union of cosets. And let's maybe look at this first one. We take H times each of these. You might argue with the disjointness claim here, but maybe I can talk you into it. We take H times C K1, HC K1. Hey, HC and H are the same, so we can replace the HC simply with H, and we get HK1. So what we get from here is ultimately this collection, and this is a collection of right cosets of H and K. You know, right cosets are disjoint, so there's where the disjointness comes in. And what we've done is written HK as this disjoint union of right cosets of H and K. How big are these cosets? These are all the same cardinality. They're all the cardinality of H, say. So what we have is n of these sets, disjoint, each being of cardinality, the cardinality of H. So we get for the cardinality of HK, we get the cardinality of H times the number of these things here, which we have as n. N was introduced on the previous slide as this particular cardinality here. It was cardinality of K divided by the cardinality of H intersect K. Let's maybe run back and look at that real quick. N was represented by this parameter here. So we're substituting that in for the n, and that was the claim in terms of cardinalities. Next result stated in the notes, no preamble to it, just a statement of it. So we'll go straight to the proof. It says if H and K are subgroups of G, then the index of H intersect K in H is less than or equal to the index of K in G. If the index of K in G is finite, then we get equality between these two things if and only if G equals KH. So what we're looking at here, I don't find this one particularly intuitive, but what we're looking at here is some properties of these KH sets as they relate to values of indexes. Okay, so we'll let A be the set of all right cosets of H intersect K in H. If we're, if you will, counting cosets of this and that, well, the number of cosets of this and that is the index of this and that. And that's what the index was by definition. So the cardinality of set A is the index of H intersect K in H. That's something we want to talk about. That's why we've introduced that. Let B be the set of all right cosets of K and G. That would, the number of those would be the index of K and G, because that's the meaning of those symbols. So by the way, the cardinality of set A is this thing, and the cardinality of set B is that thing. That's just the symbols we're using. We're going to define a mapping from A, the set of right cosets of H intersect K and H, to B, the right cosets of K and G. We're going to do it as follows. So define phi mapping A to B as phi of, okay, it's taking in a right coset of this subgroup of that group. So what we'll get is that this subgroup times, on the right, an element of H. So these are what the right cosets of H intersect K and H look like, where the little h, of course, is from subgroup capital H. And we're supposed to get out right cosets of K in G. So we're defining phi as this. Indeed, it takes the correct kind of thing in, and it gives a correct kind of thing out. That's a right coset of K and G. It's multiplied on the right by H, but H is an element of G. So we're getting some of those right cosets of K and G out. We've defined phi in terms of representatives. Okay, this coset, H intersect K, multiplied on the right by lowercase h, we very explicitly use the lowercase h in the definition of this phi. So what we need to show is if you use a different h from the same coset, you're going to get out the same thing from the function. Well, define this. Different representatives in of the same coset produce the different produce the same output. Different representatives from the same coset produce the same output. This has nothing to do with one-to-oneness or anything like that. This is well defined. Okay, so we need to confirm that phi is well defined by taking different h's and making sure we get the same thing out. So suppose we take capital H intersect capital K times H prime, which is the same as capital H intersect K times lowercase h. In other words, we've got two different representatives from the same coset. H prime and H are from the same coset, are representatives from the same coset of H intersect K. Then having right cosets equal means we've got right congruence between H prime and H, modulo H intersect K, or in other words, H prime H inverse is in H intersect K, corollary 1.4.3 part 3. The right congruence stuff, that's the best way to remember it. It wasn't stated explicitly using the terms right congruence when right cosets are equal in the corollary, but the symbols were the same, and it is right congruence. It's easier to remember in terms of right congruence. Right cosets are equal if and only if we have right congruence of the representatives. So let's see, we have this relationship under the supposition that these two things are equal. That means H prime H inverse is in K. In fact, it's in the intersection over here. So in particular, it's in K. So if we take this and interpret it as right congruence. We've got H prime is right congruent to H inverse modulo K. So corollary 1.4.3 part 3 again. Right congruence means right cosets are equal. So if these two are right congruent modulo K, then the corresponding right cosets are the same. Right congruence implies equivalence of right cosets. And similar, of course, with left congruence. So we get KH prime equals KH. Now we're dealing with this mapping defined as given here. Phi of H intersect K, H was mapped to KH. So what we'd have here is phi of H intersect KH prime would give us KH prime. Phi of H intersect KH would give us simply KH. But hey, KH prime and KH are the same as we just showed. You put different representatives, use different representatives in this location here, doesn't matter. They're from the same coset, you'll get the same output. So this really is a well-defined function. Some technicalities on well-definedness. Now, we were trying to show something about cardinalities. So we got a mapping. We'll use some one-to-oneness properties of it to draw conclusions about cardinalities, as we must. In the first sentence, nobody said nothing about anything being finite in that first statement. So I have to deal with cardinalities in terms of bijections. So next, suppose phi, and we shifted gears here, and I'm using the H primes and the H's in a different argument. So next, trying to show one-to-oneness. So suppose I put this thing into phi, and I put that thing into phi, and suppose we get the same thing out. Suppose these inputs produce the same output. We want to show that the inputs are the same. I want to show this coset and that coset are the same. That'd be showing one-to-oneness. So put H intersect K, H prime into phi, H intersect K, H into phi, and suppose the outputs are the same. What output do you get over here? Well, phi maps these kind of things, takes the deal and sticks it on the right of K. So what we'll get out here is KH prime. What we'll get out here is KH. Supposition of equality of outputs. So we get this equality here between these right cosets of K. Hey, you got equality of right cosets of K, then those representatives, H prime and H inverse, must be right congruent. That is, we must have H prime, H inverse in K. Well, H prime, H inverse is then in H intersect K. The H's came out of H. So of course, H prime, H inverse is in H. We just showed H prime, H inverse is in K. So that's how we draw the conclusion of the H prime, H inverse is in H intersect K. And lo and behold, that's right congruence modulo H intersect K. So interpret this as H prime is right congruent to H inverse modulo H intersect K, and you interpret right congruence as equivalence of right cosets, corollary 1.4.3 stuff. So that means the right cosets, H intersect K H prime and H intersect K H, these right cosets of H intersect K must be equal. That's what right congruence gives you. So we've shown if the outputs are the same, it turns out these inputs had to be the same. So those right coset inputs to phi had to be the same if we had equality of the outputs. That's the property of one-to-oneness. So phi's a one-to-one function. Phi maps A to B in a one-to-one way. The domain of phi can be at most as large as the range of phi. Or in other words, the index of H, the index of H intersect K and H, the cardinality of set A, is less than or equal to the cardinality of set B. Have to deal with these cardinalities in terms of mappings, one-to-one mappings, onto mappings. bijections if I'm trying to show equality. I had nothing with finiteness, so I got to deal with bijections there. So we've, by having the one-to-oneness, shown the cardinality of set A is less than or equal to the cardinality of set B. Oh, remember, we created these sets such that the cardinality of A was this index and the cardinality of B was that index. Stated it verbally, though didn't write it in the write-up. Okay, so that was the first claim. So we've got this index is less than or equal to that index. Second claim, if the index of K and G is finite, then the index of H intersect K and H equals the index of K and G, if and only if G equals KH. Okay, so they're saying we've got a finite index here, and they're giving us conditions under which we get an equality. We had established an inequality. Here they're showing when that inequality is an equality. Well, with an extra little hypothesis. They're giving you a necessary and sufficient condition for equality to hold. So that's how the second part's relevant to the first part. Okay, so suppose the index of K and G is finite. That was our situation for the second part. Then we've got the cardinality of set A equals the cardinality of set B, which we represented in terms of these indices. We've got equality there if and only if that phi function we had upstairs is not only one-to-one, but also onto. That is, it's a bijection. So this conclusion drawn if and only if phi is onto. So the second claim in the theorem holds if and only if phi is onto. Now the finiteness is used here in some of this if and only if stuff. So we want to show onto-ness. Phi mapped us. Where did phi map us? Let's go back and look at that. Phi mapped us into set B, this set of all right cosets of K and G. Right, so I'm looking for right cosets of K and G. Trying to see that we get all of those out. We're trying to show onto-ness of this phi function. All right, so we'll choose an arbitrary right coset of K and G. In other words, we'll choose an element, arbitrary element G, lowercase g, from big group capital G and discuss the associated right coset. If phi is onto, then K sub G is a right coset of K and G. Sorry, if phi is onto, then for this right coset of K and G, we have phi of something equals KG. So we're assuming onto. We want to draw the conclusion of equality. Well, there's what we want to draw. Equality of G and KH. And that was a statement. Let's look back at that too. Back to the previous slide. We're trying to show equality of the cardinalities in this setting, if and only if G equals KH. So what we're trying to do is take the onto-ness and relate it to this equation. All right, so we've chosen G to give us a right coset. If we have onto-ness, then we want to draw this conclusion and then reverse the argument, assume this, and draw a conclusion of onto-ness. But if phi is onto, then there's something in set A, that is, there's a right coset of H intersect K that under phi is mapped to G. Then, let's see, phi of H intersect K multiplied on the right by this lowercase h is going to give us KH. That was the definition that we had. So I know this produces KH. We'll get equality of KH with KG because we've assumed the onto-ness. And we get equality of right cosets when we have right congruence. So we'll get G is right congruent to H from this equality here, modulo K. So in other words, GH inverse is in K. So we've got G, H inverse in K. H itself is in subgroup H, so we can take a product of those two. That'll be a thing in K times a thing in H. So it'll give us a product, a thing in KH, capital K, capital H. The H inverse and the H, of course, cancel out, leaving us with a conclusion that G is in KH. We took an arbitrary element of G and showed it's also in KH. So we've got G as a subset of KH, set theory argument. I need to reverse that to draw a conclusion of equality. But of course, hey, remember H and K, they were subgroups of G. So this set of elements is going to be a subgroup of G. I mean, everything's going to be a subgroup of G. G was a big umbrella group in which all this was happening. So pretty easy to reverse the set inclusion and draw the conclusion of equality of those sets. That is, if phi is onto, then we get G equals KH, half of the second claim. Lastly, we need to reverse the hypotheses. Suppose G equals KH, and we want to draw a conclusion of, here it is, phi is onto. So now, secondly, suppose G equals KH. Let KG be a right coset of K and G. Remember, we're trying to show onto-ness now. We've assumed G equals KH. So for the G we've got over here, used as a representative for this right coset, we know that G equals KH for some K in subgroup K and some H in subgroup capital H by this assumption. So we get G represented like that. Now we've got KG, right coset, can be written as K times KH, representing G in this form, which by the hypotheses we can do. So substitution for G, the quantity KH. We've done this before. I've got subgroup K. We're going to multiply on the right by an element of that subgroup. That'll just permute around the elements of that subgroup. It'll produce the same group. I've said it in the past, the group capital K sort of absorbs the element lowercase k. And we get this kind of set equality here because lowercase k is in group K. So we get that sort of absorbed. And now we've got KG equals KH. We had phi of H intersect K subgroup times element H was KH, the very definition of phi. We've just shown that K sub G equals K sub H in the second case. So we got equality there. We chose an arbitrary right coset of K and G. We chose the KG up here, K lowercase g up here. And we've shown it's the image of something. And we've determined then that KG is the output of something from the phi function. It was an arbitrary right coset, and that's where we're mapping 2 into set B. So function phi is onto. So we've shown if phi is onto, then part 1, G equals KH. Secondly, we've shown if G equals KH, then phi is onto. There's your if and only if in the second part. Phi is onto if and only if G equals KH. And that was a conclusion of the second part. Okay. One final thing, this one's a briefer. I don't know that there's a lot of intuition to this one so much either. The first one we did, I thought was a bit intuitive. I don't know about these others. Dealing with relationships between indexes. Proposition 1.4.9 says let H and K be subgroups of finite index of group G. Okay, this is a little subtle, maybe worth some observations here. When you say in any of these groups are finite, we're saying the indexes are finite. It's a totally different thing. Remember the integers mod m are a subgroup of index m in the integers, yet the integers is an infinite group. So the indexes can be finite and the groups be infinite. So we've got finite index, H and K, subgroups of finite index in group G. In other words, this index, K and G, is finite, and this index, H and G, is finite. That's what the first sentence there hypothesizes. The claim is, then the index of H intersect K and G is also finite, and that index is less than or equal to this product of indices. Products of cardinal numbers, yeah, in general, but remember, we've assumed these indices are finite. We have finite indexes for H and K. In other words, these are finite numbers. So if I'm so possessed, I could maybe even take quotients for these things. Furthermore, we get equality here if and only if G equals HK, and we'll get the bulk of that work done by the previous theorem. Okay. First, we've got K intersect H is a subgroup of H, intersection of subgroups or subgroups, and H is a subgroup of G. Theorem 1.4.5 said when you have a big group, a middle group, and a little group, we get this relationship with the indices. In Theorem 1.4.5, the little group was denoted with a K, not with this intersection stuff. But anyhow, this is the little group, middle group, big group, to which we're applying Theorem 1.45 and drawing the conclusion that the index of the little group in the big group equals the index of the middle group in the big group times the index of the little group in the middle group. Sort of some, if everything was finite, we'd see, we could express these in terms of cardinalities and actually do some cancellation. So it's suggestive, this index notation. So we get this relationship here. Not what we're after, right? We want this index less than or equal to the index of H and G. There you go, index of H and G times the index of K and G. We want it less than or equal to. We've got an equality, but we've got this thing, not the index of K and G. But proposition 1.4.8, the one we just did, said the index of H intersect K in H is less than or equal to the index of K and G. So we had that from the previous result. So we can take this and replace it with the index of K and G. We pick up an inequality and draw the conclusion that the thing on the left is less than or equal to this times that replaced with this. Exactly what we were claiming. So there's the inequality that takes care of the claim in the second sentence. Furthermore, you get equality if and only if G equals HK. Yeah, you get an equality here if and only if you get an equality here. And you got an equality here if and only if we had G equals KH. And we required some finiteness of indices as well. And we've got these things finite. If you've got these things finite, we've certainly got this thing finite as well. And that takes care of section 1.4. So all we had was those last three little results to hack through the proofs. Next, we'll take this coset stuff and look at making groups out of the cosets. We'll look at making quotient groups in section 1.5. The Fraley book I like so much for senior level algebra calls them factor groups, and they got their reasons for calling them that. Quotient groups is a more common term. So section 1.5, we'll look at some quotient group stuff, and it's a topic that you've seen in senior level algebra already, and it's a little abstract. Ain't all this stuff. But I'll see you in section 1.5 here after a while. Have a nice day.